Today we're going to continue to talk about thermodynamics. We are now ready to introduce the third law of thermodynamics. The third law of thermodynamics is telling us that the entropy of a perfect and pure crystal is zero at absolute zero. Why is that? If we have a perfect crystal, and by perfect we mean that there are no impurity, every component of the crystal, so we can have an ionic crystal, so there would be ions, or it could be a covalent structure, but every unit in the crystal has a very predetermined and fixed position, respect to which cannot move. Now, we've seen with the molecule of water in that animation that even if the molecule of water per se is not moving, but there are constant vibration, so that the bond length between hydrogen and oxygen is oscillating around a certain average value, and then the angle, we know that the molecule of water is bent, so it's about 109, it's a little bit less than 109.5, but it's also oscillating around that value. So, but that depends on the temperature. The kinetic energy is directly proportional to the temperature in Kelvin. That means that if the temperature is 0 Kelvin, kinetic energy is also 0. So if you remember the definition for number of microstate, right? This is the formula that you use. So if so the entropy is directly proportional to the number of microstate. The number of microstate is W, and K is the constant, the proportionality constant. So if we have one possible location for each atom, atoms are all identical because the crystal is pure, and we don't have any vibration, any movement, because the kinetic energy is 0, then there is only one microstate. Then the value of W is 1, the logarithm of 1 is 0, therefore it doesn't really matter what K is, multiplied by 0 is 0, so the entropy is 0. So that's our real baseline, right? So when we talk about entropy, we are arbitrarily set, when we talk about enthalpy, the changes in enthalpy, H, we set arbitrarily the 0 to the level of the delta H of formation of elements. And we made the parallel with the elevation of a place. And we said, well, the elevation of a place would be the distance from the center of the Earth, but because we have no way to measure that, we take an arbitrary baseline that is the sea level. And that was what happened with the enthalpy. Here is like we are actually able to measure from the center of the Earth. We have an actual absolute measurement of enthalpy because we know where the entropy is going to be 0. It's going to be 0 for a perfect crystal at 0 Kelvin. So it's kind of easy, right, to mess up the words entropy and enthalpy. They kind of sound alike. And that was actually a deliberate choice of Clausius, who decided that it was going to be a cool idea to have two similar names for two different things, and I'm not sure I completely agree. Okay, so we can define the standard molar entropy with a very similar set of conditions that we use for enthalpy, right? Excuse me. So in order to be able to talk about absolute entropy, we need to have 1 mole of a substance. If it's a solution, it needs to be 1 molar. The standard state is going to be a temperature of about 25 Celsius, so 298 Kelvin. That's, let's say, room temperature, just because it's convenient to conduct experiments at room temperature. And the pressure, at least in chemistry, is going to be 1 atmosphere. It's not a proper unit for the international system, but chemists are a creature of habits. Now, you need to keep in mind that the units of entropy are different from what we've seen for energy, like internal energy and entropy. These are joules divided Kelvin. So you also have divided mole because we defined that per 1 mole of substance, right? And that was happening also for enthalpy. The enthalpy of formation refers to the reaction where you're forming 1 mole of the product. But what's really different here is this K. So the units are joules divided by temperature. The other important difference is the value of entropy at absolute. That's why there is no delta here, right? There is no delta S, it's an actual S. It's important that you understand the difference of standard condition between thermodynamics and gas law, especially in a situation of a cumulative test, like the exam you will have at the end of the semester, because then you have in the same test problems about gas law and problems about thermodynamics, so you have to go back and forth. So in the standard condition for thermodynamic, the main difference with respect to the gas law is the temperature. For the gas law, the standard temperature, STP, standard temperature and pressure, is 0 Celsius. That is 273 Kelvin. You're dealing with gas, so even if you have a liquid, if you have water, an aqueous solution at 0 would freeze, but you're dealing with gas law, so you don't care about that. Excuse me. Instead, for thermodynamic, we prefer to work more comfortably at room temperature, so that would be 25 Celsius. That give you the 298, right? So the main difference is the temperature, room temperature for standard condition for thermodynamic, and 0 Celsius in the case of the gas law. The pressure is 1 atmosphere in both instances. In chemistry, we just stick to the atmosphere as a unit of pressure, even if it's not a proper international system unit. You can see down here that the proper unit would be Pascal. This is a conversion between atmospheres and Pascal, so it takes about 100,000 Pascal to make an atmosphere. The Pascal is Newton divided square meters. So you may see a different approach in a physics or in a thermodynamic class, because in general in those classes they tend to use Pascal. That it's actually more proper. So the another quantity that's kind of convenient, and if you can remember it, it comes handy for the gas law, is that the volume of any gas, of 1 mole of any gas, in standard condition is going to be 22.4 liters. So here you have a table of value of entropy for some selected substances. So you can see some pattern. So first of all, the units, right? Joules divided Kelvin, divided mole by divided Kelvin. So that's a big difference. Also the lack of a delta here. These are absolute values. Note that we're using joules most of the time for enthalpy and another state function. We will use kilojoules. There's going to be in the next slides, you will see a bunch of formulas where you will have to combine those different things and do some calculation with it. So we'll have to do calculation that involves both enthalpy and entropy. And you need to be very, very careful with the units, because some are going to be in joules and some are going to be in kilojoules, and that's one of the most common mistakes. So if we look at the numbers, what we see is that there are no zeros, because these are standard, so we are not at 0 Kelvin. We also see that there are no negatives for the same reason. The entropy can only be positive because we have an absolute 0. Right? If we, again, let's do the parallel with the elevation. We have negative values of elevation, like as I told you in class, my hometown, because my hometown is below the sea level, and the sea level is the arbitrary baseline that we took. If we would be measuring from the distance of any point on planet Earth from the center of the Earth, there wouldn't be any negative. There would just be 0 at the center of the Earth. So entropy is in this type of scenario. Then we can compare, for example, graphite and diamond. We know that the stable form at room temperature is graphite. So, for example, when we go to look for delta H of formation, the delta H of formation is 0 for graphite, but is not 0 for diamond. So actually transforming graphite in diamonds is an endothermic process. In this case, we see that the graphite has a higher level of entropy than diamond. Why is that? Well, diamond is a crystalline structure with a very ordered structure. Graphite has less order, therefore it makes sense that the entropy is a larger value. Let's compare, for example, two substances in the same substance in two different states of matter, like bromine liquid and bromine gas. So the one that's stable at room temperature is liquid. The gas has more disorder because the molecules are free to move respect to each other. So consistently we see a higher value of entropy. Let's look at CO and CO2. That's too dark of a highlighter, but you can still see probably. So CO2, so it's very similar, but there is an extra atom of oxygen. So we go from 2 atoms in the molecule to 3 atoms. So 3 atoms allows more possible distribution, positioning during those vibrations around angle and bond length. So we see consistently a larger value for the CO2 than for the CO. If we compare two biatomic molecules, so same number of atoms, same state of matter, but nitrogen is bigger than hydrogen, so there are more electrons, more neutrons, we see again a higher value. Well, that's going to be interesting. Let's compare to alcohol. So this is methanol, and this is ethanol. So similar categories. They all have a chain of carbon and hydrogen, and then at the end there is an OH that's what makes the substance an alcohol. And also, as you have learned in Gen Chem 1, is the site where you can have a nitrogen bond. So the difference is that ethanol has more atoms, so has a larger molar mass. Consistently, there is a larger value of entropy. So we are kind of seeing all those patterns that we learned to recognize before. This table gives you a set of values for 3 common thermodynamic variables for a bunch of substances, 5 substances, that kind of randomly chosen just to give you a sense of the patterns. So you may notice that there is a degree sign at the top of these 3 variables, and that means in standard conditions. So that means that the pressure is 1 atmosphere, the temperature is 298 Kelvin, 25 Celsius, and the if anything is dissolved in water, that's the case for fluorine and calcium, then the concentration would be 1 molar. Then you also see the letter F for 2 of the variable. That means formation. So that means that and you also see that they also have a delta in front, while entropy does not. So this refers to a change in the value that happens in correspondence of a very specific reaction, that is the formation reaction. The formation reaction is when you combine the elements to form 1 mole of substance. So let's look at these 3 variables one at a time. So first of all, we have enthalpy. Enthalpy is defined as the heat exchange in condition where the pressure was constant. And you see that there is a value of 0 for the elements. And this is the arbitrary reference that we have taken. And we measure everything with respect to that. So we see there are 3 negative values here. The change in enthalpy can be positive, it just happens more, it's just more rare. And so in this 5 example that I chosen, it didn't happen to have a positive value, but it can totally be positive. Now delta G, G is called free energy. We haven't talked about that yet, but it will come. But whatever it is, we still don't know what it is. It behaves very, very similar to delta H, right? So it has the same definition. So it's a change. It refers to a formation reaction. The units are the same. And most of the values are negative, but it can be positive. And we will worry about that eventually. It will come. But S is quite different, right? So for S, we don't see any zero, because 0 would be the value when you have a perfect crystal at 0 Kelvin. Here we are at 298 Kelvin, so no zeros. Most of the values are positive. Let's say theoretically negative doesn't really make sense because we have an absolute zero, that is the pure crystal, so how can something be below? If you notice the pattern, the two negative values are ions in aqueous solution, right? So the two troublemaker are these. So what happens when you have ions in aqueous solution? You know, I could have, so if I want to measure the entropy of calcium, I could have calcium fluoride, I could have calcium sulfate. Well, that would be very poorly soluble. I could have calcium chloride, I could have calcium hydroxide. So the problem is I cannot separate the negative from the positive ion in an ionic compound. So it's hard to measure just the calcium out of its context. So we need to take a different reference for ions in aqueous solution, the reference being H+. So we set that to 0. And so the fact that calcium has a negative value with respect to hydrogen, it means that for some reason is more ordered. And hydrogen is less ordered. So the same happens for fluorine. So it's not really something that you have to worry about, but I don't want you to get, let's say, confused. If you're looking at this table and you see this negative value, and you say, well, if 0 is the entropy of a pure crystal at 0 Kelvin, how can something have a negative if we can go below 0 Kelvin, right? So it's sort of a arbitrary decision, if you will. So let's see an example where we have to calculate the delta S of the reaction where ethane, that is an hydrocarbon, it's burning. So we have the combustion of ethane. We know it's a combustion because there is oxygen as a reagent and you're forming CO2 and water. So it's a complete combustion. It goes as far as it could be in terms of the type of products. So if the problem would have been to calculate the change in enthalpy, delta H, you would have known how to do it from thermochemistry by using the Hess's law. You take the delta H of formation of the products, you multiply each by the coefficient in the balance equation, you put those numbers together, and then you subtract the delta H of formation of each reactant multiplied by its own coefficient. Now we can do that because enthalpy is a function of state, and but S is also a function of state. So we can apply with some little modification the Hess's law to S as well. What are those modifications? You see that the delta of reaction is the same. So the side, let's say, the right side is written in the same way, because in both cases we are measuring the change during a reaction. But for the enthalpy, we have a delta of formation. So these values refers to a reaction where you're forming the compound from the elements. Well, here we have absolute values as taken from the table. Now, normally, if you do this problem as one of the homework assignments, and so you have sampling and you click and it opens up a window with a table with all the values, and you need to pick the right one. Normally in a test and also in the final, you don't have like separate pages with the tables, you just get the values that you need in the question. So let's pretend we are in that sort of scenario. So we get the 4 values, and note that we do have a value for oxygen because even if it's an element, it's only for delta H that the delta H of formation of an element is 0. There is an entropy, an absolute entropy of H element. So all you have to do really is plug and chug. So remember to multiply H by the coefficient, and you get this value, and I leave it to you to check the algebra. You get a value of 619.4 negative. So why is it negative? What does it mean that it's negative? it means that the products are more ordered than the reagent. And why is that, right? So we've learned in earlier then how to compare product and reagent and decide which one has more order. We need to look at the temperature, we need to look at the state of matter, we need to look at the molar mass, etc. In this case, the critical thing is the state of matter. So, and you want to focus on the gas one, because that's where the most disorder comes from. Like a gas has much more disorder than a liquid and a solid. So when you're forming gas, that has a huge impact on the overall evaluation of the S. So we have 4 molecules of gas on the product side, while on the reactant side we have 7 plus 2, that is 9. So the number of molar gas is going down. That means that this side has more order than the other side. And that explains why the value comes up negative. So does that mean that it's not spontaneous? No, because this is the change in entropy of the system, the reaction. What's important is the change in entropy of the universe. And for that, we need to know what's happening to the surrounding. Now, if we are burning stuff, we are giving off heat, the surrounding temperature will be going up, and that will increase the disorder of the system. So we have one component that's bringing up the disorder, the other component is bringing down the disorder, so it depends which one is prevailing. In order to be able to predict the spontaneity of a reaction, we need to know both what's happening in terms of entropy to the system and what's happening to the surrounding. So with the ice cube example, we have figured out how to relate the change in entropy of the system, the change in enthalpy of the system, and the temperature. So with that kind of reasoning, one could come up with the following formula, right? So this formula allows us to calculate the delta S of the universe if we know the delta H of the system and the delta S of the system. That means the delta H of the reaction and the delta S of the reaction, because the reaction is the system. And we know how to do that with the S's law. We learn how to calculate the delta H of reaction in thermochemistry, and we just learn how to calculate the delta S of reaction with the same approach with the S's law. The temperature, you can just measure it with a thermometer, so we can get all those 3 numbers and manage, therefore, to calculate this. And this will tell us if the reaction is exothermic or not, right? Because if the reaction is spontaneous, the delta S of the universe is going to go up, so it's going to be positive. Because of the minus sign that we have here, considering that the temperature is always positive because it's measured in Kelvin, there are no negative Kelvin, this product is going to end up negative. Okay, so there is a bit of a twist with the sign that gets really confusing after a while. Okay, so you need to be careful to that. If the reaction is non-spontaneous, then the delta S of the universe is going to be negative because it's getting more order. Because of the minus sign, when we multiply by the positive kelvins, this product is going to be positive. So if the reaction is non-spontaneous, this product is going to be positive. So it's been the product between temperature and delta S of the universe has been given the name of delta G of the system, and it's called Gibbs free energy, and it's a function of state in itself because it's a product of a function of state and a temperature. So it's a function of state. So that's why we use the capital G. So it's kind of more convenient to have just one symbol as opposed to a multiplication. So the equation that you need to keep in mind is this one, and this is given in the cover of the test. So the delta G of the system, the delta G of the reaction, the free energy of the reaction, can be calculated by taking the delta H of the reaction and the delta S of the reaction and T. So this is where I was telling you that you will have to combine delta H, that's typically in kilojoules, and delta S, that is typically in joules. So the most common mistakes you will do while using the formula is to put together apples and oranges and keep one in kilojoules and the other one in joules, and to forget that the temperature needs to be in Kelvin. So let's recap. For the reaction to be spontaneous, the delta S of the universe needs to go up. That means the disorder is increasing. So the product of T delta S with a minus in front is going to be negative. Delta G is going to be negative. So for the reaction to be spontaneous, we want the delta G to be negative. For the reaction to be non-spontaneous, the delta S of the universe is going down because the universe is getting more order. So when we multiply by T and we change the sign, this is coming up positive. So delta G of the system for non-spontaneous processes is going to be positive. So from a practical point of view, delta H represents the potential energy stored in the system in forms of like chemical bonds and so forth. But the second law of thermodynamics tells us that we cannot, even if the reaction is exothermic and is giving off that energy, we cannot use it all to produce work. Delta G is the amount that's free available to do useful work. And then there is an amount, that's T delta S, that represent the energy that's unavailable. Is sort of the fact of life that there's going to be a loss in terms of heat. So Gibbs free energy is the maximum energy that is released by a process when the temperature is constant, and we can use the free energy to produce work, right? So I want to stress again the importance of paying attention to the units, right? So the entropy is going to be given in joules, because those are typically small temperature values. The temperature needs to be absolutely in Kelvin. So most of the time in the problem, they will give you the temperature in Celsius because they want to check if you remember to do the conversion. The delta H is typically in kilojoules, so it's going to be these numbers are going to be 1,000 times larger than those. So you need to equalize this. Either you transform the enthalpy in joules or you transform the entropy in kilojoules. That will determine which unit you get for the Gibbs free energy. So for reactions that are spontaneous, right, then there's a delta G that's negative. Remember the enthalpy, right? When a reaction has a negative enthalpy, we would call that exothermic, because the thermic, so the heat was going off, was going out. For delta G negative, that means spontaneous, we are going to call it exergonic, because ergo, that's the work is going off, is going out. For a reaction that's not spontaneous, delta G is positive, is going to be endergonic. Because if I want the reaction to happen, it would have to be me providing energy to make the reaction happen. For example, when you want to make electroplating, that's a non-spontaneous reaction, you need to connect your system to the power supply. Okay, so there is a parallel between exothermic, exoergonic, and endothermic, endoergonic. The direction is the same, represented by exo and endo root. What's changing is that the last part of the word, ergonic, means to refers to delta G, refers to work that can be done. Thermic refers to heat that can be exchanged and refers to delta H. You bet there's going to be a question about that. Similarly to what we did for enthalpy, H, where we define the standard delta H of formation of a substance, we can do the same for delta G. So they behave very, very similarly. The one that's a bit on its own is entropy, S. Okay. So for delta G of formation is going to be the free energy that we experience when we are forming 1 mole of a substance starting from the elements. And the same as we did for delta H, the delta G of formation of elements, if they are in the standard state, the most stable allotrope, standard pressure and temperature and so forth, is going to be 0. And because G is a function of state, we can use the Hess's law. So the delta H of a reaction can be calculated as the difference between the delta G of the products, I'm sorry, I said the delta H. The delta G of a reaction can be calculated as the sum of all the delta G of the products, each multiplied by the coefficient that's in front of the balanced reaction, minus the sum of all the delta G of the reactants, delta G of formation, each multiplied by the coefficient. So the formula looks a bit complicated, but what it's trying to tell you is that this means sum, because if you have 2, 3, 4 products, you need to do the math for each of them and then putting them all together. This is the fact that you have to subtract the reactants. This is the sum of all the values for the reactants, N and M represent the generic coefficient in front of each species. So let's see some values of delta G of formation, okay? And we see a pattern that's very, very similar to the delta H of formation that I show you in the thermochemistry unit. So you see that the elements like bromine, graphite, iodine is 0, provided they are in the most stable form, because if bromine is gas instead of liquid and at room temperature is liquid, then there is a different value. Diamond, that's not the stable form, doesn't have a value of 0, and the same for iodine in the gas form, because at room temperature iodine is a solid. You see a majority of negative values, and that's parallel the fact that we saw a majority of delta H values. So that means that for most substances, the reaction of formation is exothermic and exergonic and spontaneous. And this also kind of is a confirmation of the fact that the two are kind of getting along, going side by side. That initially, when we were talking about what makes something spontaneous, we said, well, the majority, not all, but the majority of the spontaneous reaction are exothermic. And this is mirrored by the fact that delta G and delta H in terms of sign, most of the time they go side by side. So now we are able to add to that picture that I showed before free energy, because now we know what it is, right? So you see that there is a strong similarity, a strong parallel behavior between free energy and enthalpy. So free energy can be defined as this product between temperature, delta S of the universe, and then with a minus in front. Like delta H is 0 for the elements, and like delta H, it's either negative or positive. And then for entropy, we've seen that sometimes there are negative values when you have aqueous solution, aqueous ions. Let's see an example of calculation. We are given a reaction and we are asked to calculate the delta G, and we have all the values for the 3 substances involved. We have delta H of formation, enthalpy, and delta G of formation. So for hydrogen, you can notice that being an element, the delta G of formation, delta H of formation is 0, but you do have a value of entropy. So we can use the Hess's law, right, and just focus on the delta G. We are a standard condition. We are asked to calculate the delta G in standard condition, so yeah, we can just take the values from the table. So we take all the delta G of the products, that there is only 1, and then the delta G of the reagents, that there is only 1 because hydrogen is 0. So the products needs to be multiplied by 1, the reagent by 2. So we get this value. Now we could have used a different approach. We could have used this equation, right? This also allows you to relate delta G, to calculate delta G from delta H and delta S. Now, of course, it takes more calculation, so it would be preferable to use the first approach, because for the second approach, I need to calculate delta H from these values. And then I need to calculate delta S from these values. So it's more, it's longer. But you should get the same number. Right, so you calculate delta H with the S's law, you calculate delta S with the S's law, and then you put those together in the formula, and you get almost the same value. Now, these values are all determined experimentally, so this table, there is a certain degree of experimental error. One book from another may have a slightly different value of delta H, S, and delta G. So this is a slight difference between this number and this number, that's in the order of the units, like it's about 2 kilojoules per mole of difference. It's compatible with the experimental error. So let's see how the different driving forces combine into determining if a reaction is spontaneous or not. So this equation is telling us that there are two components that are important, the delta H of the reaction and the delta S of the reaction. So is the reaction giving off heat or absorbing it? Is the reaction getting more ordered or more disordered? Okay, so let's imagine for a moment that the reaction is exothermic, so delta H is going to be negative. So that would be good, because if you want the reaction to be spontaneous, delta G should be negative, so having one of the two things we are summing up negative is kind of pushing in the right direction. What would we want delta S to be? We would want delta S to be positive. That means increasing disorder, because then you have to multiply by T. T is always positive because it's in Kelvin, so it stays positive, and then you multiply by this minus sign, it becomes negative. So you're adding up two things that are both negative. And this would give a big negative delta G, regardless really of the value of T. The value of T wouldn't make any difference. What if the reaction is endothermic? So we have a plus sign here. So this would go in the direction of making delta G positive. That would mean a non-spontaneous. What would be consistent with that? What would push in the same direction? It would be our reaction producing more order. So if the system is getting more order, delta S of the system is negative. That means that when you multiply by T, it's staying negative, but then you multiply by a minus sign, it's becoming positive. So you would have positive, and that would give a big positive delta G, and the reaction would not be spontaneous at any temperature. If instead delta H and delta S are kind of pushing against each other, then the temperature becomes critical, right? So these are the two situations we've seen. If the reaction is exothermic and there is an increase in entropy, then the reaction is spontaneous at any temperature. If instead the reaction is endothermic and is decreasing entropy, both things are leaning towards making the reaction non-spontaneous at any temperature. The temperature really doesn't play any role. When temperature becomes important is when you have scenarios in which delta H is pushing one way and delta S is pushing in the opposite way. So let's consider this first. If the reaction is exothermic, that is pushing the reaction to be spontaneous. But if there is a decrease in entropy, right, so that this is negative, then you multiply by T, that's positive, is going to be negative, and then you multiply by this minus sign, is going to be positive. So you have this is negative, this whole thing is positive. Which one is bigger depends on T, right? Because if you have a very large level of T, so if you are in a very high temperature, it's going to make this bigger, so the reaction is not happening. But if T is a very small number, then this multiplication, yeah, sure, is positive, but it's a very small number, so delta H becomes prevailing, and the reaction would happen as long as the temperature is low. How low? Well, you need to do the math. So if you have numbers, you can determine at which specific temperature. If you do not have the math, any number, you can still tell, in general, this process is going to be spontaneous at low temperature. The opposite happens if you have an endothermic reaction. So this is positive, it's kind of pushing against spontaneity, but the reaction is increasing the disorder. So this is positive, once you multiply by the minus it becomes negative. So you have a negative here that would make the reaction spontaneous, but you have a positive here, and that's kind of a brake, something pushing on the brakes. So you want this to be prevailing, so you want a large value of T. So in this condition, the process is spontaneous at high temperature. So, as I said, to actually determine at which temperature things are going to switch from spontaneous to non-spontaneous, you need to do the math. But sometimes they ask you a question where math is not needed. So let's see some example. The incomplete combustion of carbon is described by the following equation. How does the spontaneity of this process depends upon temperature? So what they're trying to ask you is this spontaneous at any temperature? Or is this non-spontaneous at any temperature? Or maybe the temperature needs to be either high or low to make it spontaneous. So that's the type of answer. Why does it say incomplete? That's sort of it really doesn't affect your answer. It's one of these information that are there for sake of writing a correct question, but it's not really relevant for you. So you even ignore it. The reason they're saying incomplete, right, is that you don't form CO2. When you have a complete combustion, you form CO2. And that's what you want in your furnace at the house. If the combustion is incomplete, due to scarcity of oxygen. So oxygen is the limiting reagent, and that would happen when your furnace doesn't receive enough supply of oxygen from the outside because there's a blockage, for example. Then instead of forming CO2, you form CO because you have less oxygen. CO is toxic, and that's a common cause of more lethal accidents in houses during winter time if the heating system is not being properly maintained. So the fact that combustion is incomplete, they say it's kind of relevant if it's your furnace. In this problem, it doesn't really, it's more of a confusing extra information. So you may think, oh my gosh, I don't have any number, how am I supposed to make any decision? Okay, so but because there are no numbers and because there is no calculation, this is supposedly a short problem to solve. That means it makes it a favorite for final and comprehensive tests. Just because it doesn't require math and is potentially short, it doesn't mean it's easy. It's short if you know what you have to do, right? So what you have to look at here, so the formula that you want is the delta H, the delta G is equal to delta H minus T delta S. And you want to evaluate the sign of those variables. You don't have the number, so you cannot do the math. But you can still make a guess, an educated guess on the sign. It's a combustion, and you know because there is oxygen here. If it's a combustion, it's exothermic, right? So if it's exothermic, delta H is negative. You don't know how much it is, but you know that's negative. Then you make an evaluation about S, okay? So you go from 1 mole of gas to 2 mole of gas. So the disorder is increasing, delta S is positive. So you know also the sign for delta S. So now you have all you need to put in that equation and make some guess, right? Because if delta H is going to be negative, right? So this is negative. Delta S is going to be positive. So once you put the minus in front of this, T is always positive, so this is going to become negative, so it's negative and negative. So delta G is going to be negative at any temperature. It doesn't really matter, you know, T can be big, can be small, this is going to be spontaneous at any temperature. Let's see another example. So we need to use the same approach. This is the combustion of ethane, right? So if you remember, this is the same slide, the same problem we put in slide 9. In slide 9, I give you the numbers, you could do the math. Here you don't have the numbers, you can only make a qualitative assessment, like a general yes or no. So it's a combustion, so it's going to be exothermic. This time you have a decrease in the number of gas moles because you have 2. and 7, that's 9, and here you have 4 because water is liquid. So the moles are going down, so the entropy is going to be negative, the change in entropy is going to be negative. So here you have negative, that's going to be multiplied by another negative. So at the end of the day, this is coming up positive. This is negative. So negative and positive, they are going opposite ways. What the sign of delta G is going to be depends on the temperature. If the temperature is small, this positive component is teeny tiny, and therefore you have a negative. If the temperature is big, then this is going to be bigger than that, and therefore delta G is going to be positive. So for this to be spontaneous, you need low temperature. Now, that seems a bit counterintuitive because it's a combustion, you know, but consider that if you're above 100 Celsius, that's highly likely when you're burning stuff, this would probably be a gas, and that would change the whole path, because in slide 9, you would have to have used the enthalpy of formation of and the values in general. The values from the table should have been from gas H2O and not liquid H2O. So the numbers would have come up different. In this reasoning, if this would have been a gas, you would have gone 4 plus 6, 10 moles against 9. So the amount of gaseous species was going up. Delta S would have been positive. So it would have all been a different picture. Okay. So for each reaction, there is one and only one value of standard delta G of reaction. For the same reason, there is one and only one delta H of reaction, and that can be calculated with Ayer's law. You need to remember that the standard condition means that the concentration of each of the species is 1 molar. So normally, if we have an equilibrium reaction like the one presented here, right? Very rarely the equilibrium constant is 1. Most of the time is a different value. It's not impossible, it's just very rare. So if the concentration of each of the species is 1, it doesn't really matter what the exponents are here, C and D and B and A, because 1 elevated to whatever is still 1. So everything is 1. The product, the reaction quotient, is going to be 1. And it's going to be typically 99% of the time is going to be different from the equilibrium standard. So the system in standard condition is not at equilibrium. So how this is going to affect our reasoning. So if the K equilibrium happens to be big, let's say 10 to the 5th, right, then Q is too small. So Q needs to increase until it reaches the equilibrium constant. In order for Q to increase, you have to increase the amount of the reagents, C and D. So the reaction will move to the right, and we would say that the reaction is spontaneous. If the equilibrium constant is particularly small, let's say 10 to the minus 5, then Q, being 1, is too big. The reaction needs to move to the left, so it is going to increase the amount of reactants and decrease the amount of products. That means that the reaction is not spontaneous. It is not surprising, therefore, that there is a relationship between the standard free energy of the reaction and the equilibrium constant of the reaction. The relationship is the one shown here. You don't have to worry about memorizing it because it's going to be given in the cover of the exam, as well as the one in the other page. So delta G is going to be the free energy in kilojoules. T is the temperature in Kelvin. The equilibrium constant does not have units. Ln is the natural logarithm. What about R? R is the gas constant, but which one are you going to pick? You're familiar with two values. One is in joules divided moles per Kelvin, the other one is in atmosphere liters divided mole per Kelvin. So the 0.082 is the one you used in the gas law, Here you are going to use the other one because you want consistency with the units, and so you're calculating delta G in joules. You want the R constant to be in joules. Okay, so let's look at the minus sign. So you see that there is a minus sign in front of R, right? So let's imagine we have a big equilibrium constant, let's say 10 to the fifth. That means that there's going to be, by the time we reach equilibrium, much more products than reactants. So the reaction is favoring the products. If the K equilibrium is a big number, the logarithm of a number that's larger than 1 is going to be positive. So because of the minus sign in the equation, you're going to make it negative. So therefore, you will have a delta G negative. That means the reaction is spontaneous. That makes sense. It's consistent with the fact that it favors the products. If the reaction has a very small equilibrium constant, by the time you reach equilibrium, you have a lot of reactants. An equilibrium constant less than 1 means that the logarithm is going to be negative. The negative in the logarithm plus the negative in the formula will make a positive. You will get a value of delta G that's going to be positive because the reaction is non-spontaneous. If by accident you have one of those few reactions that have an equilibrium constant of 1, then by the time you reach equilibrium, the two concentrations are going to be the same, right? So that would give you a ratio of 1. The logarithm of 1 is 0, so the delta G would be 0 because you would be at equilibrium in standard condition. So what if you are in a non-standard state? That could mean, for example, that the concentration of reactants or products are not equal to 1 molar, and maybe the temperature is not 298. So we are going to make a correction. So the actual value of free energy in non-standard condition is going to be equal to this value in standard condition, so this one, and minus an adjustment that keeps in mind the temperature and keeps in mind the different concentration, so the reaction quotient, right? So remember that delta G in standard condition can be calculated with this formula, and then the reaction quotient is calculated using this formula. So by the time you reach equilibrium, the reaction quotient is going to be equal to the equilibrium constant. Therefore, these two terms are going to be identical, and delta G is going to be 0. So at equilibrium, the delta G value is going to be 0. So just because a reaction is spontaneous, it doesn't mean that it proceeds completely to 100% of products and no reactants left. It's a bit situation like having that rock on top of a hill, and there is a second hill. So if you let it go down, you reach this position of equilibrium, and then the rock will probably oscillate back and forth a little bit until it stops into C. If you would start from B, you would have the same exact ending point. Okay, so A is the represent potential energy of our reactants, B the potential energy of the our products, and the equilibrium position is intermediate between the two and is going to be reached regardless of the point you're starting from. So the final thing we are going to cover is coupling reaction. So in our body we have a lot of reactions that are performed thanks to the presence of enzymes. These enzymes are proteins that make reaction happening faster. They make happening in a more specific way. They also make a reaction happening that would not be spontaneous. So breaking down food, that's basically combustion, generating heat, that tends to be spontaneous. But metabolic processes that build up complicated molecules like proteins, imagine putting together, growing up and making up more muscles, those are typically non-spontaneous. So how can we perform non-spontaneous reaction in our organism? And the trick that the living system uses is to use spontaneous reaction to push non-spontaneous reaction. It's a drive force. So this process is called reaction coupling. So let's say we have a reaction that we want to make in our body, putting together a molecule A and molecule B to make a bigger molecule C, but that reaction has delta G that is positive and is not spontaneous. So the trick is to perform two reactions. In the first reaction, we're coupling A with, we are adding to A a phosphate using ATP. And then in the second reaction, we use this activated molecule of A to react with B and get what we actually wanted. And so by the end, putting together two reactions, we also we had two things happening. The reaction we wanted, it was A plus B giving C, that was non-spontaneous, but we also performed a second reaction, that was the hydrolysis of the ATP. There was a spontaneous one that was pushing anything else. So it's a bit like, using your car to pull your trailer. The trailer being the reaction that we want to make, and the track being the ATP. So by putting the whole two together, the delta G is overall negative, and we can manage to do the reaction. So let's see a practical application of a coupling reaction with the synthesis of sucrose. Sucrose is the result of putting together two simpler sugars that are called monosaccharides, glucose and fructose. Fructose takes its name because it's a typical sugar that you find in fruit. So as you see, the molecules are kind of complicated. So we can simplify our life and represent them with a geometrical shape due to the fact that the molecules itself, they are actually closed in a cyclic structure, right? So we can represent glucose with an hexagon and fructose with a pentagon, and then when they are together, they form a bond through an atom of oxygen. So the reaction of putting together glucose and fructose, it has a positive delta G, so it's not spontaneous. But we can take advantage of the ATP hydrolysis that is spontaneous and actually has a larger value, absolute value, like 30 is larger than 27. So when we put them together, we end up with a net of -3 kilojoules. So we still have that's the driving force basically. So let's see how it works, right, with this example. So the uncoupled reaction of glucose plus fructose cannot be performed as such because the delta G is positive and is not spontaneous. So the trick is to couple it with the hydrolysis of ATP. So in the first reaction, you have that ATP is hydrolyzed so that one of the units, phosphate units, is attached to the glucose, so you get glucose phosphate. This product of the first reaction becomes the reactant of the second reaction. So it's an intermediate because it's making you're producing it in reaction 1, but then it's going to disappear in reaction 2. So it's an intermediate, and it's a shared intermediate, and that's the trick that keeps things running. So it's going back to the example of the truck and the trailer, you need to hook them up for the truck to actually be pulling the trailer. So the glucose phosphate represent in a way the hook that keeps the two things together. So that's the end of our presentation, and that's the end of the thermodynamic unit. So it's important to remember that there is the need for a shared intermediate in order for the coupling reaction